Hello, today I'm going to be discussing the problem longest repeating substring and how we can solve it in linear time. In order to solve this problem in linear time, we have to use a couple different algorithms. First of which is DC3, or another lexicographical suffix array construction algorithm that takes linear time. And once we have that suffix array, we use the Kasai algorithm to get the LCP array, which can then be used to get our final answer. First step of the DC3 algorithm is to construct the sample. For this example, we're going to use a string t, which is equal to the word banana with a dollar sign at the end. First step to setting up our sample is that we have to split the string into 3 separate containers. And to do this, we're going to use just simple mod 3 of the index of each part of the string. We have like I said, 3 different containers. We got zero. First one has 0, 3, and 6. Second one has 1, 4, and 7. And the last one has 2 and 5. 7 in this case is just a blank suffix with nothing in it, which is useful for something later on. And then we can let S of I denote a suffix starting at index I and T, and let C be the union of B1 and B2, which will be the set of sample start indices which we'll use, and S of C is a set of sample suffixes. The second step for DC3 is to construct R, which we can then use to sort the sample suffixes. Or let T of I be the ith element of T, and for K equals 1 and 2, we construct the strings where R of K equals T of K plus 1, T of K plus 2 as a triple, and then keep going up until we get to T of max B of K, T of max B of K plus 1, and T max B of K plus 2. And what do R1, R2 look like? As you can see, we have R1, which contains ANA, a dollar sign, and then a blank one with empty characters. R2 has NAN, an a dollar sign, and a blank character. And we can concatenate these two strings into a string called R, and then the non-empty suffixes of R correspond to S of C of sample suffixes. By sorting the suffixes of R, we get the order of the sample suffixes S of C. So the next step, of course, is to sort the characters of R. We can sort this by using radix sort the characters using by the triples, and then rename them with their ranks to obtain a new string R prime. As you see, we order them lexicographically. So the blank suffix is ranked number 1. Then we rank by the ones that start with A. And the dollar sign goes before any other normal alphabetical character. Then we go to the next A and then continue onwards. And we got the ranks and their indices in R. And after that, we can sort the suffixes of R. And if any of the characters of R are the same, we have to recursively sort them. In our case, since none of them are the same, we don't have to. We just can set up these tables which connect the index of R and the suffix to their rank and the start index of the suffix in T. Next step is to use the sorted order of R prime to sort the sample suffixes of T. And we can do this by combining the results in the last 2 tables. We can see that we can assign a rank to each suffix in S of C. As you can see, there are some suffixes that are blank. These are the ones that were in that were in B0, which were not in our samples. In order to sort the non-sample suffixes, we have to represent each of them by a tuple, which includes the T of I and the rank of S of I plus 1, which is the rank of the one right above it or below it. And that gives us this representation. We got index of 0, which is B in the string, and as you can see in the table, the suffix with index plus 1 of 0 is 3, so we add rank 3, and then we can compare these suffixes as follows by this rule, which basically translates to if t of I is less than or equal to t of j, then that means s of I, and if t of I is less than t of j, that means s of I is less than j. If those are equal to each other, then you have to then check the ranks. In our case, it's very simple to sort them because we have just none of the same characters, so we sort them by the characters. We don't have to worry about the ranks. So the sort order we get is S of 6, S of 3, and then S of 0. Finally, we just have to merge all of these parts together. And to merge, we can use these rules. To compare a suffix S of I, which is in B1, with a S of j, which is in B0, we can use this rule, which works very similar to the previous. And then if the suffix S of I is in B of 2, and we want to compare that with S of j, which is in B of 0, we have to have the extra rule to add the extra characters, since B of 2 is 2 characters away from B of 0. And this eventually gives us, once run through, this gives us the final suffix array, which starts at 7, 6, 5, and goes 3, 1, 0, 4, 2. This is the suffix array that we will need to use in our Kasai algorithm. Analysis of the algorithm. Correctness of this algorithm can be easily checked by doing the suffix array by hand, assuming sample size is manageable. In the runtime of this algorithm, each part of the algorithm can be done in linear time except for the recursion done when multiple suffixes have the same rank, which would give t of n equals t of 2n over 3 plus big O of n. And after resolving this, you end up with the big O of n, which means this algorithm does indeed run in linear time. Now that we have the suffix array, we can now start with the Kasai algorithm. The first step of this algorithm is to find the length order of the suffixes in the suffix array. This can be done by taking the length of the original string and subtracting the size of the suffix, which can then give the index which each of the suffixes would be in the length array. This would end up giving this array. And the next step is then we just move down this array and find the LCP for each one. And the first of which is banana $, which is rank 5. So move over to rank 5 on this array, and we check this one, and we check the one above it and see if there's a common character at the start. In this case, there's not, so we can give this LCP a 0 and cross out the B, because we know since the size is decreasing, the first character each time is removed. There will never be a B considered again, at least in this B. And then we can also cross out the LCP of the first array, or the first index in this array. Since there's no value above it, it cannot have an LCP. And the next step is to move on to the next suffix in the length array, which is this one, which is rank 4. So move down, go to rank 4. We check the one above it. It matches the A, which is good. And then we match the N as well, which means the LCP is at least 2. We check the A, also matches. Then we check the next character. This, however, does not match. So now that we know that 3 of them match, we know that for the next, very least next 2 LCPs, there will at least be 2 or 1 of that matching characters, since we are moving one character each time. So we set the LCP to 3, move on to the next one, which is this one, which is rank 7. And since again, in the previous one, we already checked the N, we already checked the A, we just need to check the next character, which in this case does not match, so the LCP is just 2. And then we move on to the next one. Again, we cross out the N, so we know at the very least the next one will have an LCP of 1, since the A's will match. And then we move on to the next one, which is rank 3. Again, we know the A's, we don't need to check the A's again. So we check the N, does not match, so it has an LCP of 1. And then we move on to the next one. And now that we cross out the A, There's no guarantee that the LCP value will be greater than 1 or greater than 0 in the next one. So we check rank 6, we move down, N just on match B, so that one would be 0. Cross out the N, then we check the next one, ace $, move check, doesn't match, 0, and then the next one is also 0, so it's matching with a blank one. Then you can define the answer to the original problem we were talking about. All you need to do is find the max value within this LCP array, which in this case is 3, which means the longest common prefix is 3. Analysis of the algorithm. Each character of the original string is only checked once by this algorithm, which means it runs in O big O of n runtime. This means the algorithm runs in linear runtime like DC3. This means that since both the DC3 algorithm and cost-size algorithm can be run in linear time, the LCP of a string of characters can also be found in linear runtime. Thank you.